There's also a very interesting result that we can actually derive for expectation of a function of a random variable. Okay, so we've been talking about x as the random variable. Okay, let's just say now that if we are thinking about a function of my random variable x, okay, let's just say we're using g as a function expression. Okay, and I'm starting with x as the discrete random variable, and then g is a function applied to the random variable x. So I'm using capital Y as the new random variable, which is the function of my x, okay, in terms of g. So y equals to gx. So if I have this, the result that we're showing over here is really useful, interesting. It's saying that if I know the PMF, okay, so notice here, I start to use a subscript of capital X just to differentiate, because now we have another random variable over here, right? So we want to make sure that we're talking about the PMF of x over here, okay? So PMF of x, if I know the PMF of x, this result is telling me that I can actually get the expectation of this function of the random variable gx, which is in terms of y, through this result. Okay, so what this is telling us is that the expectation of y, or expectation of gx, whichever way you do it, actually equals to the sum of gx, which is y, okay, and multiplies with the PMF evaluated at x, okay, and then I sum them up for all of the possible values where the PMF is greater than 0. Okay, so this is super handy. Okay, let me show you what I mean by super handy. Let's just say x is a discrete random variable with the following PMF. Okay, you can take 3 different possible values, -1, 0, and +1. The associated probability, which is the PMF, is going to be 1/4 for -1, 1/2 for 0, and then 1/4 for +1. Okay, now I'm defining a new variable, which is actually a function of x, which is x squared. I'm asking you to compute the expectation of y. Okay, so, well, based on the result that we just saw, y is x squared, right? And earlier we're writing it generically as gx. Okay, so essentially we are trying to do expectation of gx, okay, given the PMF of x. Okay, so if we follow the result that we had earlier, okay, expectation of gx, okay, is, we know, thinking about all of the possible x where px, x is greater than 0, right? And then we have gx times px, x. Okay, so if I follow this, okay, just do it one by one over here. We have the PMF handy over here, right? And then our function y is x squared. So this is saying that we are doing x squared, right, times, because that's gx, times pxx, okay? And if I bring it back with this particular example, I'll have my -1 squared, because that's x squared, multiplies with 1/4, because that's the probability associated with x equals to -1, plus 0 squared, okay, that's this part over here, times 1/2, and then plus this one, 1 squared times 1/4, which if you do the algebra, it's going to be 1/2. Okay, so this is handy, like I said, that, well, if I know the PMF of x, I can not only find out about its expectation using the previous result that we saw, the current result is telling us that we can also find out about expectation of functions of x. Okay, so x squared, square root, x cubed, any kind of thing that you want. If you know the PMF of the random variable x to start with, and then if you want to know the expectation of a function of it, you can apply this result. I would just also add that check out the textbook, okay? They have a really nice proof over there to show why this is true, okay? So yeah, get the chance to do that to deepen your understanding.